Welcome to my talk on implementing an extensible renderer. It's been a while since I spoke about my rendering project called Rafix, mainly because I haven't been actively working on Rafix. 2022 was a very busy year for me, so I haven't had as much time to work on it. That said, this break from Rafix has been a good opportunity to think retrospectively about the last couple of years that I've worked on it. I want to focus on some ideas that I think are worth sharing, instead of talking too much about Rafix itself. I'll touch on some things in Rafix to make concrete examples, but I think this talk is more interesting if it's useful to people whether or not they want to use Rafix. First, some background on the project. I wanted to make a viable start towards a renderer that could be used in real shipping games. To me, that means productive workflows for implementing rendering techniques and getting content onto the screen. This was also a learning project for me. My experience in graphics before this project was a little bit of DirectX 9 in university on student projects quite some time ago. Modern rendering APIs today are quite different from what was available at the time. When I started the project, it was Vulkan only, and I was focusing on the basics, like rendering quads, some normal mapping, and eventually some very basic lighting. I worked with Carl Bergstrom, who had a project at the time that would eventually become Distill. It implemented file change detection and provided a way to process assets and stream them to a remote device. In this demo, all of the assets like textures and meshes are streamed to the mobile device. And when I change the scene in a text editor on the PC, it streams changes to the device. After hitting this milestone with a fairly dirty prototype, I spent a lot more time on foundational aspects of the renderer. I transitioned from working directly with Vulkan to having separate backends for Metal and Vulkan, and eventually GLES 2 and 3. I also added a render graph, some rendering techniques like shadows, and a better pipeline for handling shaders. I also spent some time learning how to use Blender and writing a custom exporter to get full scenes out of Blender and into the renderer more easily. In this demo, the scene is exported via the custom Blender plugin, making it much easier to iterate on. In late 2021, the overall architecture had taken shape. I implemented a second pipeline for higher fidelity rendering to take advantage of newer hardware, while still having some support for web and older hardware. I was able to implement a lot of new rendering techniques quickly, using the tools and workflows I had built over the previous year. I'm especially happy to have implemented GPU-driven rendering with occlusion culling, and implementing my own TAA was also a great learning experience. I'd like to briefly pause and give some encouragement to anyone who may be just getting into graphics programming. My experience with learning has been very rewarding, and looking back, I think the difficulty is not that any one topic is necessarily hard, just that there are a lot of topics. But this means they can be tackled one by one. Time and persistence can lead to real progress. Now I'd like to discuss some specific ideas in graphics that make it extensible. First, the crate structure is incremental, adding functionality and optional layers. Plugins allow new functionality to be implemented non-invasively. I'll focus on two of the three plugins that exist in Rafix in this talk. Finally, I'll discuss the extract and render resources, which allow plugins to share data with each other and the application without unnecessary coupling. The core rendering logic in Rafix is split into 4 layers, with plugins that add functionality. The layers can add functionality and helpful utilities, but become more opinionated. The responsibility of the layers are clearly defined and they aren't cyclically intertwined, so you can use what you need and ignore the rest. First, Rafix API implements an API abstraction layer. The internals are left exposed, so it's easy to work directly with the hardware API when it makes sense to do so. Next, the framework layer adds a lot of helpful utilities, such as a render graph, delayed resource destruction, descriptor state management, and a pipeline cache. It also includes the shader processor, a utility that reads GLSL code and generates compiled shaders, reflection data, and Rust source code that provides strongly typed APIs that greatly ease producing data to be consumed by the GPU. The asset layer adds distill as a dependency, allowing code to load an asset by path or ID and related GPU resources to be automatically created. The renderer layer sets up a swap chain and render thread and provides a skeleton that the plugins can hook into. Graphics comes with several plugins and a Blender extension for exporting whole scenes. Users can also add their own plugins. And finally, the application creates the window and enables the required plugins. The first kind of plugin I want to discuss is the feature plugin. A lot of what it does is based on this talk. While I'll mention a few of the concepts from it, please check out the original material. A render phase is a time to draw things, usually during a render pass. For example, the skybox, the shadow maps, opaque, transparent, or UI. A render feature is a thing to draw during one or more phases. For example, a mesh, a tile map, a skybox, or things like that. A view is like a camera, a frustum, and which phases should be drawn. For example, the mesh render feature may draw during shadow map, opaque, and transparent render phases. There might be a view per shadow map, which just enables the shadow map phase, and a single view for the scene that enables the skybox, opaques, transparents, and UI. The outcome of this is that the shadow casting meshes are rendered to the shadow maps with one shader, while for the main camera view, the meshes are drawn in the appropriate order with a different set of shaders. All features are drawn in 3 steps. First, we extract the data we need to draw the frame from game state. Next, we do any CPU side work required before emitting draw calls. For example, we might have a claw simulation. Finally, we emit the draw calls to command buffers. I've left out a lot of details, but to touch on a few key advantages. This architecture allows unrelated rendering features to coexist. It also allows a render pipeline to control when the features draw, all of this with as little coupling as possible. There are many other advantages. Please check out the full talk for more details. Next up are pipeline plugins. And here I mean pipeline in the sense of steps to draw the frame. For example, Unity has 2 pipelines, the lightweight and the high definition pipeline. The role of the plugin is to schedule CPU and GPU work needed to draw the scene. Only one is active at a time. Typically, the plugin will define and execute a render graph, but this isn't required. It could be arbitrary code. A lot of resources are available to read about render graphs. I think they make a lot of sense if extensibility is at all a priority. In graphics, the render pipeline plugin generally produces a render graph per frame. The parts of the graph that are active will change depending on game state as well as graphics setting. AMD recently introduced render pipeline shaders, which I think are worth the look as well. They showed some very promising results. Making this concrete, Graphics provides 2 pipelines, which are really generating 2 render graphs, with a lot of the same render phases and features. The basic pipeline is highly compatible, while the modern pipeline is more forward-looking. That said, they still share a lot of code. The takeaway here is that a lot of basic functionality can be shared even while supporting multiple pipelines. Finally, I want to talk about extract and render resources. The purpose of this system is to support passing data between the application and plugins, as well as between plugins. This will be familiar to anyone who has used an ECS. Arbitrary structs can be inserted and looked up by type. Sharing data in this way reduces coupling, as it avoids the assumption that a specific plugin is being used. It only requires coupling to the struct, which is acting like a contract for the kind of data to be shared. Implementing this doesn't require much code, and it's easy to find example implementations of it. Graphics has two flavors of resource maps. The extract resource map is rebuilt every frame and just has references to game state. Render resources are persisted across multiple frames and mainly used to share data within the render thread, or to pull data from the render thread back to the game thread. So for some example use cases, an application can publish data to plugins, such as setting a graphics option like enabling or disabling bloom. A plugin can publish data to other plugins, such as a pipeline plugin, pushing shadow maps to the mesh feature plugin. Plugins can also publish data back to the application, such as debug data. To summarize, render features allow sharing and reuse of basic stuff that many of us need. Definitely check out that GDC talk. Render graphs and pipeline plugins can control rendering features without direct coupling directly to them. And a resource map allows for sharing data without too much coupling. I also think this allows for batteries included approach to make a render more approachable and productive, while also being flexible enough for power users. As for what's next, I think renders are more fun when they have content to draw. And managing that content, particularly in a way that lets people work in teams, is very hard. I think a solution, in the form of a content pipeline with tooling, could be Rust's killer app for game development, and a potentially good inroad for Rust to be used in commercial games. But this is hopefully another talk for another time. Best wishes in the coming year, and thanks for listening.